Okay, so let's get started. Hello, everyone. Thank you all for joining us for today's technical talk about the state of artificial intelligence and machine learning in the petroleum industry. My name is Hossein Izadi. I'm the president of SB student chapter at the University of Alberta. And I'm very interested personally in the application of machine learning and machine vision in subsurface engineering and like geosciences generally. And one of the person that inspired me to walk in this way was Professor Mahathir. I follow him for like 10 years when I was just an undergrad student, and it led to like many papers, patents, and software. And I'm now a PhD student here at the University of Alberta. The University of Alberta is the oldest, has the oldest petroleum engineering program in Canada, and it's only the only accredited undergrad petroleum engineering program in Canada. And The UAV Petroleum Engineering program ranked between the top 10 QS world world university ranking by subject in petroleum engineering. And it's our great pleasure to have Professor Mohammed with us today to give us a technical talk about the application of and basically the state of the artificial intelligence and machine learning in the oil industry. I'm sure that you guys already read the biography that I already shared in my LinkedIn page and also in the invitation letter. He's the pioneer in the application of artificial intelligence in the exploration and production industry. And he's a professor in West Virginia University, and he's the chair and the president and the founder of ISI company. And I just want to add something that I personally know about Professor Mohammed to the biography. He's a philosopher, you know. He has the ability to think. He knows how to think about a problem, how to approach to solve a problem, and down the road, how to think to solve a problem. And this is a character of a developer. And we are very happy to have Professor Mohammed with us today. And Professor Mohammed, thank you for your time, and the stage is now yours. Sorry, you are muted, Professor. Awesome.
Thank you. Thank you very much for the introduction, and it's very nice to be here with all of you. Very quick question before I get started. How long do you want me to have my presentation in terms of time? And I'll follow literally exactly as much as you ask me to.
This thing is yours, you know, because it's scheduled, the meeting is scheduled for like 2 hours.
Okay.
In addition to the question and answer session. And everyone can send the question to my PV chat. And at the end of the presentation, we will move to the Q&A session.
Very good. Okay, thank you. Thank you very much. So I'll try to keep it definitely no later than an hour and a half. I will show you the topics that I'm going to go through, and then we'll leave half an hour for conversation and any question that you might have. Let me go ahead and share my screen, please. Please let me know if you can see the screen and I can get started.
Yes.
Okay, very good, thank you. Okay, so this has to do with the state of AI and machine learning in petroleum industry. It's honestly quite different from a lot of presentations in this area that you will hear from. And I'll try to explain why and what is the reason, and go as much. So let me go ahead and tell you the outline, what I'm going to cover. I'm going to start talking about what AI and machine learning is, which is, to me, in the context of oil and gas industry right now, this is the most important thing, because one of the unfortunate things that I have come across a lot is that it seems not to be a good understanding of what this technology is in our industry. And I'll show you why I say that. It's not just a claim. I started actually doing research in this area, AI and machine learning, when it was not called AI and machine learning, in 1990. So it's almost 31 years. That's another very important thing, knowing the history of this technology. What was it called at the beginning? When did it turn and started being called artificial intelligence, and so forth? If you have questions, I can go ahead and provide as much detail as you want. So I'm going to provide some definitions of what this technology is, and then I'm going to talk about what petroleum data analytics is, which is the application of this technology in our industry. And then after these two, which are not going to be very long, I'm going to talk about the state of this technology, AI and machine learning, in our industry, petroleum industry. there are 5 topics that I think are very important that I have to talk about. One has to do the difference between what artificial intelligence is and what traditional statistics is, because both of them use data to perform analysis. Another one has to do with engineering application of artificial intelligence and machine learning, because everybody thinks what Google is doing or what Facebook is doing, we can do exactly the same thing. And there's a difference between engineering application of this technology and non-engineering application of this technology. We talk about that. Then I'm going to talk about modeling physics using artificial intelligence. After that, I will provide some information on what's called explainable AI or explainable artificial intelligence. Last, it's going to be talking about the ethics of artificial intelligence and how it's used in our industry, whether there are enough ethics in it or not. But so what I'm going to do, I'm going to make sure that at the end, I'm going to take 15 minutes and talk about one, because everything that I'm showing to you right now is not necessarily showing you a problem solving very specifically in oil and gas industry, which is how I have been dealing with. To make everything I was talking about in the first hour, in the last 15 minutes, I'm going to talk about geoanalytics, which is AI-based geological modeling. For those of you who have done reservoir engineering, I'm sure you will enjoy this. This is a reasonably recent thing that we have done. So that's the context that I will be talking about. So first, let's talk about definition of artificial intelligence and machine learning. And the question is, why do I come up with a definition? The reason literally is that a few months ago at JPT, I saw an article. JPT is Journal of Petroleum Technology, as you all know, for Society of Petroleum Engineers. They had a article, and in that article, whoever wrote it, they provided the definition of artificial intelligence and machine learning. And that's literally was quite shocking to me, that why would people define it in that way? That's why I thought it's very important for us to see what the definition of this technology is. The definition that I'm presenting to you, it's not my definition. This is the definition that provided by those people who have generated and developed and created this technology. I think it's much more fair to get that definition than something that we think or some other people think what it should be today. So in that context, what is artificial intelligence? Artificial intelligence is the technology that simulates human intelligence. That's very obvious, right? Artificial intelligence, which is human intelligence that is created in artificial fashion. So that's very, very simple, right? So that it's a technology that simulates human intelligence, and it does it, the key is this, it does it by mimicking human brain and for analysis, modeling, and decision-making. This is a very top definition. I'm gonna go into a lot more detail in a minute. The next one is machine learning. What is the definition of machine learning? Machine learning is the science of making computers to act without being explicitly programmed through using open computer algorithms and learning from data. That's a lot. So let me provide a little more detail so you can see what I'm talking about. So first and foremost, it says it makes computer to act without being explicitly programmed. Right? Think about it for a second, because as I'm talking about petroleum engineering, so let's talk about reservoir engineering as a good example. So when you do numerical reservoir modeling, what do? Literally, you tell the computer what to do. You want it to act. However, you tell the computer what to do and how to act in incredibly explicit detail. Simple, I mean, literally word for word, so detailed, multiply this by this, calculate that, so and so, move it to this direction and calculate that and multiply it by that. So you tell it exactly. So in other words, the non-machine learning algorithms, or what we do, let's say in numerical reservoir simulation, we tell them exactly what to do. The computer doesn't do it for itself. That's the difference. In machine learning, we use an open computer algorithm. The same algorithm can be used in multiple different problem solving. The only difference is the amount of data you provide. The same algorithm uses the data from reservoir, solves it. The same algorithm uses the data that you provide from drilling and solves it, and every other things that you do. So the computer algorithm is completely open. However, and it's not explicitly, you don't tell them exactly what to do. However, it learns it from the data of what to do. And another word that is very important is the machine learning, right? So the question is, what is learning, right? Because the word machine is very obvious when we're talking about, but learning is the key word that we have to discuss it. And you as students know that when you take a course, right, you try to learn, right? Is it possible to learn without teaching? Think about that for a second. Think about a course that you take, and imagine that your professor comes in and gives you 2 books and 25 papers. And the first day that he or she meets you, and they tell you, okay, welcome to this course that you took with me. Here's the books, here are the papers, and I'm going to meet you at the end of the semester to give you a final exam, right? So it gives you what you need to deal with, but is he or she teaching you? No, it's not teaching you, because you take another course and the professor comes in and he or she tells you, okay, yes, here's the book and here's the papers, but we're going to meet twice or 3 times every week, and 1 hour or 1.5 hours, we're going to discuss. I'm going to teach, you're going to ask questions, I'm going to give you I'm going to solve problems, show you how to solve the problem. I'm going to give you homework, you're going to solve the problem at the homework and come back and show it to me what you did, wherever you, and back and forth, until we get to the end of the semester and we get you the final exam, right? So the question is, are these 2 types of courses the same? Definitely not, right? In both of them, you're learning. Yeah, in both of them, you're learning. But in one of them, direct teaching is taking place. In the other one, there is no direct teaching. They give you the book and you got to go and learn on your own, right? So think about that, because it's very, very important to think about that, to understand what's the difference between machine learning and the other types of, or how statistics does it. So keep that in mind. We're going to come back and talk about that. Finally, deep learning is a learning from data by pattern recognition using artificial neural networks. So let me go a little bit more detail on what artificial intelligence is. Artificial intelligence mimics nature in general and solves complex and dynamic problems. Human brain is constructed by evolution. That's another thing that you will become very, very important, interested in as you learn AI, evolution. So it's constructed by evolution, human brain, to deal with uncertainties and various possibilities, right? Different possibilities. Okay, one of the algorithms that used very extensively in the artificial intelligence is artificial neural network. What does artificial neural network does? Artificial neural network mimics the neurons in human brain for the learning process. And learning through pattern recognition by using data to train a series of open computer algorithms and identify the connection between all the neurons that it has created for the neural network, right? So this is what artificial neural network is. It mimics the neurons in human brain. However, there is another technology that's called fuzzy set theory. But fuzzy set theory that also mimics human brain, but not the neurons in the human brain, rather the logic of human brain, because that's what's called fuzzy logic. It avoids the limitation of two-valued logic in order to expand the potential the potential to learn and make reasonable decision based on non-exact information. So think about it, when you make a decision, how many of decisions that you make are based on yes, no, black, white, 0, 1, two-valued logic, Aristotelian logic, two-valued logic. Human brain does that, but very limited. Overwhelming majority of the decisions you make are somewhere between yes and no. It's somewhere between black and white. It's somewhere between two things that must be done. Thousands of things can be done between them. That's called multi-valued logic. So that's when the human brain logic goes into, these are, the courses are taught on that, but I'm just providing a very simple example of that. So that's another algorithm of artificial intelligence. Another third algorithm that at least I'm not saying only these three algorithms are part of artificial intelligence, but these are the three that I have been using for in the past 30 years. And the third one is genetic algorithm, which mimics Darwinian evolution theory, and its job is to optimization purposes. And it's an evolutionary computing. It's a process that finds solution and performs optimization of very, very complex problems. And it does it through natural selection, which is Darwinian evolution theory. And again, there are courses that we teach on that. And if there are questions, I'm going to go into the detail of that. But these are the three main algorithms of artificial intelligence. One of the things that I would like to mention is, in order for you to make sure, if you become enthusiast in artificial intelligence and machine learning, one of the things you find out, in order to find out whether you really became an expert in it, is look at the type of information and interest that you find in philosophy, in neuroscience, and in computer science. These are the three major parts of the type of technologies that you will end up becoming incredibly interested in if AI and machine learning is what you are planning to learn. Of course, you will learn biology, you will learn statistics and mathematics as well. However, the key is philosophy, neuroscience, and computer science. So with that, that's a very simple way of definition. Now let's talk about petroleum data analytics. What is petroleum data analytics? What it is, it's an application of artificial intelligence and machine learning in petroleum engineering. And the main thing is it uses data as starting point, as the foundation, as the main building block of analysis, workflows, modeling, and decision-making. This is very, very important. You may all know that we always use data. In the past 70 years that we use petroleum engineering, we use data. Excuse me. However, the way we used to use data, it's very, very different than how we use the data in context of petroleum data analytics, which is AI and machine learning. Simply, for most important thing is because the way we use it traditionally in engineering and petroleum engineering specifically, the way we have been using data in the past 70 years, data is there to serve our understanding of physics. So we come up and we model the physics first, and then think about Darcy's law, think about diffusivity equation that you use, think about every mathematical equation that represents a physical phenomenon that you have learned. Think about it, because then you look at the equation and you say, diffusivity equation tells me I need permeability. Go and measure permeability. It says I need porosity. Go and measure porosity. So data is there to serve our understanding of physics. We identify what we need, and then we go and get that data. Historically, traditionally, in AI and machine learning, in petroleum data analytics, exactly opposite of that. Data is not there to serve our understanding of physics. Data is there for us to model the physics. Very different from how traditionally we model the physics. I'll talk about that. It has nothing to do with mathematics. It has nothing to do with mathematical equation. It does have to do with mathematics, but not with mathematical equation. That's how traditionally we did that. We'll talk about that in a minute. What petroleum data analytics is not, that some people think it is. They think it is very much similar to traditional statistics. It is not. PDA has nothing to do with, I take that back. I'm not saying it's nothing to do. It is not traditional statistics. Keep one thing in mind, folks. Traditional statistics was generated 110 years ago, more than a century ago. What we call artificial intelligence today, that has been generated for what it is today. That was generated in 1986 that we're using it today. So they cannot be the same. And I actually have some slides to go into more details. Another problem, a lot of people think it's an IT problem. It's an IT discipline. It is not. IT discipline is the use of computers to store and retrieve data and information. That's not what petroleum data analytics or artificial intelligence does. It's not an IT, specifically an engineering application. And finally, another thing that petroleum data analytics is not, is combination with mathematical equation. I'm going to talk about that as well. Petroleum data analytics, when AI is used in petroleum engineering and in other engineering, not only petroleum, you must not use mathematical equation to generate data. I'll explain to you why. Because it does exactly opposite of what AI and machine learning is for. So with that, PDA is completely changes the role of data in modeling physics. Data, as I mentioned, is not there to serve our understanding of physics. Physics is completely modeled by data, not by mathematical equation. PDA is high. That said, then people think that, okay, if that's the case, why do I need to be an engineer? Well, if you're a petroleum engineer, you'll find out why. Because physics and geology are incredibly important when it comes to petroleum data analytics, application of AI and machine learning to petroleum engineering. The same is true with other engineering. You have to have domain expertise of that. It's highly important. However, physics and geology are not deterministically and rigidly formulated. Okay, we'll talk about that in a bit more. So in general, when you're doing petroleum data analytics, you take the physical phenomenon that you're trying to model, you get all the data that is generated, not by mathematical equation, but by actual measurements. You take that and you take it to the algorithms and you come up with a data-driven model. And of course, as you may already know, this is not a one-shot process. It's a process that you go through it in many, many epochs until you come to a conclusion. One more thing that I already mentioned in a fashion, but I'm going to repeat it, is that petroleum data analytics uses hard data, not soft data. What is the difference? Hard data is everything that is actually measured. Soft data is something that you calculate that really doesn't exist. If a very, very good example of that, for those of you who are familiar with shale analytics, with shale, right? In shale, what do? When we drill these horizontal wells with multiple stages and clusters, and we hydraulically fracture it, right? So when people use RTA, rate transient analysis, or numerical simulation to model the shale production, what do? They take hydraulic fracturing for every stage or cluster. They identify a fracture half-length, fracture height, fracture width, fracture conductivity in order to do what they do. Those are not hard data because they do not exist. There is no fracture half-length. There is no fracture height. There is no fracture conductivity that you can measure in shale. Why? Because it's naturally fractured. It's not sandstone. And it's naturally fractured. Fracture goes all over the place in places that you can never see. Nevertheless, when we do RTA, that's what we do. When we do numerical simulation, that's what we do. So what does it mean? It means it's soft data. Soft data is full of assumption. It's full of simplification. It's full of biases and preconceived notion. And the key behind AI is to avoid that. Avoid assumption, simplification, even interpretation. So the hard data that's used are well trajectory, well log, core analysis, SCAL, well test, PLT, ILT, seismic attributes, completion design, reservoir stimulation or well stimulation, operational condition, everything that can be measured. With that, let's talk about the current state, which is after this. Why are we talking about that? What is the current state of AI and machine learning in the petroleum industry? In the past 7 years, the state of AI and machine learning in petroleum engineering is incredibly poor. Why is it poor? Well, the reason is AI and machine learning, for the overwhelming majority of service companies or vendors, is all about marketing and business because they able to make money out of that, and has very little to do with the reality of science and technology. And I tell you why, because this was what's interesting is that for 20 years I kept talking about that you cannot use only AI experts to do these things for you. You have to use domain experts. And then the domain expert that came, they figured out, okay, oh, I know what the mathematics behind neural network is. What does that mean? Then I am an AI expert, which is completely wrong, because they think if they understand the math of the algorithm, then they know what the AI and machine learning is. That is very, very incorrect. The mathematics that's required to know, you don't need a BS, you don't need a master's, you don't need a PhD. You literally, if you have a high school diploma, you understand the mathematics behind these algorithms. So it's less than 10% of your expertise of AI and machine learning. Yes, you must be a domain expert, no doubt about it. However, you have to learn how to use this technology from neuroscience and philosophy and computer science and so much. It's a different way of approaching and solving the problem. However, the service companies currently in our industry and a lot of vendors, they don't care about that. All they want to do is to make money. And in order to do that, they tell you whatever the company they're doing for, they tell them whatever they want to hear. And then what they do, it's literally what they do, what we've been doing the past 7 years. And it has nothing to do with AI, because they have a very little understanding of the science of this technology. So the question, how can operating company or even you and I manage the management of these company or people like you and I can realize the realistic state of AI and machine learning when we talk about service companies and the vendors that they tell you they're going to do that? Well, let's talk about that. There are two major issues associated with service companies and vendors that they do that it's cause all these poor application. One of them, which was very old, and still some of the big service companies are still doing that, is using AI expert with no petroleum engineering domain expertise to run the part of their company. And to be very honest, many big companies, big one, I'm not going to tell you their name, but I know that for a fact because I interact with them. Many of the big national oil companies and international oil companies make many big ones. The people who are in charge of their so-called data-driven part or analytics part, they're not petroleum engineers. They are AI experts. That's great. to be AI expert. But if you're not a petroleum engineer, there's not much you can do. So AI and machine learning experts, when they have superficial understanding of engineering, then that's one of the major problems. They do not realize that there are major differences between engineering versus non-engineering application of artificial intelligence. I'm going to show you in a few minutes what do I mean by that. Furthermore, the results are always poor without knowing how to teach the machine learning algorithm, as I mentioned. In history, some of the big companies in our industry have turned to hate AI because they spend tens of millions of dollars with people from Google, actually. And what they learned from them, what they received as outcome of what they paid for, it was absolutely nothing. And they said, wow, is that AI? We don't really need it. This goes back to 2008, 2009, 2010. But still, some of them are doing that. This is number one. Number two is the other way around. Domain experts with superficial understanding of AI and machine learning. How do you know they have superficial understanding? There are three possibilities. Ask them and find out. If they think machine learning and AI is the same as traditional statistics, stop listening to them. That literally in English means, if they translate that in English, I have no idea what AI is. When I talk about linear regression, I call it machine learning and AI. Linear regression, or even decline curve analysis that we've been using in our system since 1960. Some people call that machine learning right now. The other one is what they call hybrid models. As I mentioned, they combine mathematical equations. They generate the data from mathematical equation and combine it with the measurements. And then when they do that, that means they do not understand what AI is. Because literally, I'm going to show you, hopefully, if we have time to show you why I say that in the AI ethics. And finally, another problem, these are that's the two, this is number three, if you want to find out that they don't know what AI is. When they use non-engineering application to solve engineering problem. Actually, you can go and on YouTube and find some professors at some engineering tell you how they're solving the problem using what? Using convolutional neural network, who was generated by Google for image recognition. Some of them are doing LSTM. It was generated for natural language processing. When you use exactly the same thing to solve engineering related problem, that literally means I have no idea what AI and machine learning is. Am I saying that you should not learn convolutional neural network or LSTM? Absolutely, I'm not saying that. You must. However, if you learn it very, very, very well, and you are an engineer, you'll find out that is not the tool you use to solve engineering related problem. What you learn from that is how do you solve a problem using AI and machine learning? Use the approach and then take that to the engineering. So literally when we use, that's a very interesting, if you want to solve reservoir engineering, modeling using AI, what you do is not CNN, is opposite of CNN. It's not convolutional neural network, is deconvolutional neural network, because you have space and time and you have to deconvolve them instead of taking different layers that you generated through digital signal processing in CNN, in the convolutional neural network, and bring them together. It's exactly the opposite. But anyways, so literally there has been a pendulum swing in petroleum engineering. First, it was AI experts with the superficial understanding of engineering. After a while, it became exactly the opposite. It became domain expert with superficial understanding of AI. But in reality, this is what you will end up being: petroleum data analytics expert or petroleum data analytics engineer. You must be a domain expert, definitely, but you have to become an expert practitioner of artificial intelligence and machine learning, not just learning the math behind it. So with that, what is the realistic application in petroleum engineering? Main characteristics of AI and machine learning. Number one, it's quite different from traditional statistics. It's quite different. Engineering application is quite different from non-engineering application. AI uses the to model the physics without mathematical equation. I'm going to show you that. And it's an explainable AI. It's not black box, and it's ethics of artificial intelligence. I'm going to talk about those. So one last thing before I go to the next step is the AI and machine learning, unfortunately, is a lot of buzzwords. I have a question for you. If somebody company tell you that we can create a master reservoir engineering in just 1 month, what do you think? Would they say that? What, by the way, nobody says that. Don't get me wrong. But what if they say that? What do you think? Don't you think they're joking? What if they say that they can make master physicists in just 1 month? This is not real. No company has ever done such a marketing. If they say master statisticians can be done in 1 month, I just made this up to show you that it doesn't make sense, right? Now, let me show you another one. Master data science in just 1 month. This is real. I haven't made this up. All you have to do, go to the Google and find out which company does that. And that's what the buzzword is. This is a real marketing advertisement. That's my problem with this, because AI and machine learning seems all be about marketing and business. It's very little to do with science, really, unfortunately. But if you want to become an expert in that area, you have to follow the sciences. So first and foremost, one of the things I said, the AI and machine learning versus traditional statistics. Statistical analysis, folks, uses existing models to identify patterns in the data. When you say linear regression, what does that mean? It means you already made a decision, it's linear, right? And then you're going to find out whether your data matches it or not. Even when you say nonlinear, what does that mean? Well, you say nonlinear, but if you want to do a statistics, you have hundreds of nonlinear equations that generates different types of shapes, and you try to find out the data that you got matches which one of them. So literally in statistics, a predetermined pattern already identified, and they use deductive reasoning. So it matches predetermined pattern to the data deductively, following what's called Aristotelian approach to the truth. Because Aristotelian approach to the truth has to do with two-valued logic and simplicity. I'm going to talk about that in a second. Traditional statistics is all about correlation, not causation. How about AI and machine learning? This AI machine learning, this discovers existing pattern in the data to build a model. It doesn't start with a predetermined pattern to find out which one is matches that. Discovers patterns not in a deductive fashion, but inductive fashion. And I'll explain that to you in a minute. And it follows the Platonic approach to the truth. Plato versus Aristotle. Plato was Aristotle's teacher. AI not only provides correlation, but also it provides causation. And I'm going to show you explainable AI, what I mean by that. So what is deductive reasoning versus inductive reasoning? Remember, statistics is deductive reasoning, traditional, and inductive reasoning is what AI and machine learning is. Deductive reasoning or traditional statistics starts with a theory. It starts with a theory, it confirms a series of hypotheses, and then it arrives at a conclusion. Inductive reasoning, which is AI and machine learning, doesn't do that. It starts with the data, it infers conclusions from the data, and then it arrives at this conclusion or as a conjecture. A conjecture is conclusion formed on the basis of incomplete information, because the data that you have from a particular characteristics that you're trying to solve, a physical model, You don't have all the data that exists or can be generated. You have part of it. Deductive reasoning, folks, starts with a general principle, and then it goes to solve that special case that you're dealing with. However, inductive reasoning is exactly the opposite. It starts with a special case, and then it comes up with general principle. That is the main difference between statistics and AI and machine learning. So let's assume you're solving a problem using data. Let's talk about reservoir engineering, for example. If you are dealing with a mature field that has so many square miles large, and the reservoir 10,000 feet under the ground is hundreds of feet thick, right? Question, do you have every piece of data that you need from that? Of course not. You have 100 wells that produced for 10 years, for example. Is that it? Yes. Couldn't you have 500 wells? Of course you could. Couldn't you have 20 years of production? Of course you could. Do you have it? No, you don't. So what do? From the unknown function representing the reality, you only have data for training a certain amount. 50 wells, 60 wells, 100 wells, certain amount of data for a certain number of years. So you don't have everything, but you're trying to use the data that you have to model that big thing that you're trying to deal with. If you do statistics, then you set a series of hypotheses and you find out of one of those hypotheses, the final one, that matches that. When you do machine learning, that's the other way around. You don't do that. You literally come up, you use the machine learning algorithm, you provide all the data, you end up not with one hypothesis or one equation. You never come up with an equation. You come up with matrices and weights of the connections, which is literally from the human brain. That's what we are mimicking. You're coming up with synaptic connection between neurons in the brain that you're trying to build. How many? There is no equation, but if you want to turn it into equation, yes, you have 500 equations. So statistics, fitting the data to predetermined equation, machine learning discovers complex pattern in the data. That's the major difference. And if you look at it, while traditional statistical algorithms are not part of machine learning, many of these traditional statistical algorithms can contribute to certain machine learning technologies. So you have to learn them, but they're not the same. Don't just confuse them. They're logistic regression, linear regression, multivariate regression, Bayesian network, Markov chain. None of these are AI and machine learning. Supervised and unsupervised learning, neural network, fuzzy set theory, evolutionary, all of these are machine learning. They do come together to a certain degree. So after that, we talk about engineering application of AI and machine learning. What does that mean? Why do we call it engineering application? Does Google do engineering application? Does Facebook does? How about Netflix? And let's look at how about Amazon? So there are differences between engineering problems and non-engineering problems. Do you agree? Because if there was no difference between them, why did you go and got your engineering bachelor's degree and master's degree and PhD? There's got to be a difference, isn't it? So solving a non-engineering problem, solving non-engineering problem requires general intelligence. It does not require any domain expertise when it's non-engineering. However, if it's an engineering problem you try to solve, it requires domain expertise. So let's talk about, forget about artificial intelligence. Let's talk about human intelligence. The difference between solving non-engineering versus engineering problem. You have human intelligence, but that not every human can solve engineering related problem. If they want to do, they have to go at the university and go through a lot of teaching and learn that, right? So let me give you an example. You see a lot of pictures here, right? Cats and dogs. This is called image recognition, a convolutional neural network generated by. So what it does is which ones are cat, which ones are dog. Fantastic. It finds out which one are cats, which are dog. Don't get me wrong. This is very, very complex, folks. For decades, they tried to solve that. They were not able to using computers until AI and machine learning. And they were able to build a machine learning algorithm, convolutional neural network, and they solved it. But I have a question for you. That's a fantastic tool, don't get me wrong. But I have a question for you. Do you need a bachelor's degree to find out which one is a cat, which one is a dog? No, you don't. A 5-year-old can tell you which one is a cat, which one is a dog. So CNN, the convolutional neural network, it's a non-engineering application of AI. You don't need any domain expertise. You just need to have human level general intelligence. When you use your iPhone to find your face, so it doesn't have to put the password in there, face recognition. Is that engineering, folks? No. A 5-year-old knows which one is mom, which one is dad. It can recognize the faces. Object recognition. Do you need a bachelor's degree to find which one is a pedestrian, which one is a car, which one is a bike, which one is a bicycle? No. Human intelligence can tell you that. Voice recognition. A 5-year-old can tell, even if he or she cannot see, he can tell if mommy's calling me or daddy's calling me. Do you need an engineering application for that? Do you need even autonomous vehicles that right now it's going to be a big deal? Question, do you need a bachelor's degree to drive a car? No, there are people who can drive trucks and they can't even read. So driving does not require a bachelor or master or a PhD degree. Translation of one language to another, you don't have to be an engineer to do that. Caption generation. You see this? Can you tell, can a 5-year-old say what's going on here? Yeah, the 5-year-old, sweetheart, what is this? It says, oh, it's flying over the water, right? So the bird is flying over the water. A 5-year-old can do that, and you don't really need. And that's what LSTM was generated to do that. Okay, now I have another question. I have it for you. What do you see? You see a series of dark circles and yellow circles, right? So if I ask a 5-year-old and give him a pen and say, can you draw a line that separates these dark and yellow, black and yellow dots? I'm sure he or she can do it, right? However, if I tell her that, sweetheart, this is a nonlinear separation, he probably doesn't know what nonlinear means, a 5-year-old, right? I said, I want a straight line. Can you use a straight line to separate them? No, a 5-year-old cannot, but you guys can. Why? Because you have gone through mathematics. It's the nonlinear separation. If you ask for a linear separation, then all you have to do is to make a very simple calculation, and then a straight line can separate them. You see, there's a difference between domain expertise. So does human brain build? So that's said. So that is required. That said, I have another question. Does human brain builds equation and then solves them to find solution? This is what we do, right? In the past 70 years as engineers, that's what you learn. You build a mathematical equation, you solve it, and that becomes, you solve the physics, right? Does human brain does that? No, human brain doesn't build equation. It still can solve physics, right? The human brain includes dendrites, axon, and the cell body. All the dendrites are the inputs, the axon is the output, and the cell body decide whether the input can, what it can create as an output. So human beings solves the problem through observation, experience, trial and error. Solving engineering-related problem using AI and machine learning, it mimics human brain in solving engineering-related problem. So let's talk about modeling physics using AI and machine learning. What does physics mean, folks? Physics is a Greek, is derived from the Greek word physis, which means nature. So physics literally is nature. Traditional modeling of physics intends to describe the features and behavior of physical phenomenon and use mathematics equation to do it. So relevant physical principle governs the phenomenon of properties of the material that with which the phenomena may interact. So what does that mean? Literally, it means if you want to solve a physics-based problem and you want to build build a model, you want to model it, what do? First, you identify all the variables, all the parameters that describes the feature or controls the behavior of that physical phenomena that you're trying to model. And then you develop a mathematical equation or multiple of them to define the interaction, communication, and relationship of all these parameters and variables. That's what we have been doing. And then we want to solve it. If it's complex, we have to solve it numerically. If it's simple, we solve it analytically, correct? I have a question for you. When companies make things that they hit, they send it. So literally, this is the range, right? So when you have, anyways, so let me go to detail. So in ranging, when you identify when this is coming down, imagine that we were, instead of being virtual, we were in the same place together. And I would take my pen and I throw it at you. Wouldn't you catch it? Right? So in order to be able to do that, you're solving a physics-based problem. This is a physics-based problem. There is a range, there is a velocity, initial velocity, there is an angle, and there is a gravity. And this is the equation. To find the range where what I throw at you is coming down, you have to know the initial velocity I threw it at and the angle, and of course, you know the gravity, right? And so my question to you is, when I throw that at you and you catch it, does your brain solves this problem and then identifies its analytical problem, but it finds out where the ball or what I throw at you coming, and it tells your muscle, your hand, where to go and catch it? No, not really. That's not really what happens. Can human brains solve physics-based problem? Yes, of course it does. You saw American football, right? So these guys who catch the receivers, that they catch the ball that is thrown at them, are they PhD in engineering? So they brain builds that equation and solves it? No. Our brain can solve physics-based problem without building a mathematical equation. That's what AI is going to do. Does human brain construct and solve mathematical equation in order to solve this physics-based problem? Of course not. Then how does human brain solve the physics-based problem? This, what you're seeing, that all of you can do. It's very, very, very tough to do that using mathematics. You can do it, actually. It takes 6 different mathematical equations. You have to solve them continuously together, but there's no way you can solve them in real time. But you and I can do it. A 5-year-old even can do this. How do we do that? We do it through observation, through learning, through trial and error. And we use the data that our eyes and ears and senses see it. Data used by human brain is uncertain, right? We don't know at what degree or at what velocity it's going to the left or going to the right, but we know it's going fast, slow, very fast. not two logic, multiple logic. Is uncertain, the data that we deal with is full of noise. Since AI mimics human brain, can it use data to solve physics-based problem? The answer is yes, it can. It uses the same thing. So can physics be modeled by data using AI and machine learning? I'm gonna pass this one because the time is coming out. So let me go ahead and talk about, so this is the main thing, that data-driven modeling of physical phenomenon using AI and machine learning. The key behind it is there is no assumption, there is no interpretation, there is no preconceived notion, no biases, no simplification. That is its difference between how we do it mathematically. So let me explain to you a couple of other things before I go. I try to do it quickly, so I'll be finishing it in the next 30 minutes. First, let's talk about explainable AI. Petroleum data analytics incorporates explainable AI. It's not a black box. Explainable AI is one of the critical advantages of petroleum data analytics when it's compared to non-engineering application of AI and machine learning. As you probably know, the whole idea behind explainable AI came up with US Department of Defense in 2016, and it had to do with the non-engineering application of AI. We came up with it in 2010. Why? Because when we developed AI-related solutions, everywhere we presented it, all the engineers and scientists, they said, how could you do that? You have to explain it. How did you come up with that? That's why engineering application is quite explainable. Let me show it to you. If the developed data-driven model cannot be explained, then it is not related to petroleum data analytics. Why? Because this statistics analysis that presented to engineers and scientists, one of the most contentious issues usually brought up by scientists and engineers, they say, where is the causation? We see the correlation, but where is the causation? Engineers and scientists usually mention that correlation does not necessarily explain causation. Are they correct? Absolutely, yes, they are correct. Historically, all the data-driven analysis performed by statisticians are purely based on correlation, not causation. Most of the times, correlation does not necessarily represent causation. Let me show you something. Do you see this plot? What you see in red is suicide by hanging, strangulation, and suffocation from 1999 to 2009, in that 10 years. What you see in blue is US spending in science, space, and technology. Do they correlate? Yes, 99.2% they correlate. Is one causing the other one? I think it's very obvious. I don't need to say it. This is another one. What you see in blue is divorce rate in the state of Maine in the United States. What you see in red is per capita consumption of margarine. Is that what's causing divorce in Maine? Obviously not. But look, they have 99.3% correlation with one another. So just because you show correlation through statistics, that doesn't mean causation, right? So our traditional models by physics, physical phenomena, are they explainable? Very obvious, right? Can you explain Darcy's law? Can you explain diffusivity equation? Of course you can. How the results of traditional models of physical phenomena are explained. How do you explain it? If you don't have to talk, you have to show. Well, traditional models are developed using mathematical equation. Mathematical equation can be explained by performing multiple types of analysis, right? So let me give you examples. One of them is performing single parameter sensitivity analysis. It explains the impact of every parameter, every variable on the entire model. Another one is performing multi-parameter sensitivity analysis. What is that? It explains the impact of collection of parameters, 2, 3, 4, 5, on the outcome of the model. And finally, it's developing type curves as we do. Type curves are well-behaved curves that represent the detailed characteristics of multiple variables that are included in the mathematical equation that is used to model the physical phenomena. So let me show you how these three, single parameter sensitivity analysis, multiple parameter sensitivity analysis, type curves, how we can do it in AI. This is single parameter analysis, has to do with porosity. What you're looking at, folks, on the x-axis, you have the porosity. On the y-axis, you have 6-month production of a particular well. Which well? This is the well right here. You have hundreds of wells in this data. This is one of the wells. And if you say, I want to sweep that, so that well has one porosity value only. But when you build the model, then you say, okay, for this particular well, if I change the porosity from 5 to 12, what does it do to the production in this? Does that make sense? This is for this well. This is for another well. This is for another well. They're not exactly the same equation, right? But they're very, very explainable. Higher the porosity, higher the production. This is stimulated lateral lengths for shale. For this particular well, x-axis is stimulated lateral length, y-axis is production, 6-month cum production. It says that if you go from 1,500 to 6,000 lateral length, the production increases. However, for that one particular well that you're looking at, we had one value only. This is another well. This is another well. These are single parameter sensitivity analysis. Finally, proppant per stage. How much proppant do you use per stage? For this well, x-axis is proppant, which increases as you increase the proppant, the production increases up to a point, then it flattens for this well. For this well, behavior is different, but you can see the behavior, and there is explanation. That was single parameter. How about multiple parameters? This one has 2 parameters. X is water saturation, initial water saturation, Y is porosity, and Z is production. So as you can see, for this particular, you sweep both of them. So when you go from out of 2, you go to 3, 4, 5, 6, then you cannot do simple, you have to do Monte Carlo simulation. This is porosity. As you can see, porosity, saturation, lateral length, and proppant per stage. 4 different parameters. You're changing them and you run the model 1,000 times and you show them in 50. And it tells you, okay, the production now is in x-axis. In the y-axis is the cumulative probability. How much production goes as you change when you run this for this particular well. This is one well, PDDA and PEAA-D1. For that one well, you change these 4 parameters 1,000 times, and each time it gets your production and you plot it, it gives you this. For another well, finally, type curves. What are type curves? You all very well know type curves are a combination of several well-behaved curvatures. In oil and gas industry, we have a lot of type curves. Type curves are very well-behaved, continuous, nonlinear lines that represent the solution for analysis of mathematical equation that are usually used to model the physical phenomenon, right? These are the curves. Now, I'm not going to go into detail. Let me show you all the type curves that we have in our industry, right? They're very well behaved. They're not all over the place. So what does that tell you? That tells you the mathematical equation was generated. These solution was either numerical or analytical. How about AI? Let me show you what we call shale analytics. Is it explainable? Let's explain the influence of lateral length and number of stages on hydrocarbon production for different wells in Marcellus Shale in Pennsylvania. Do you see well-behaved curves? Literally, x-axis is lateral length, y-axis is production. This, all of it is for well number 2, and each curve shows number of stages. If you have 15 stages, this is lateral length change increases the production. 20, 25. This is for one well. This is for another well for exactly the same field. This is for another well. Do they behave correctly? The same thing, lateral length in x-axis, production in y-axis. Every curve here shows the proppant per stage. This is for one well. This is for another well. This is for another well. Do they look very well behaved? They explain exactly what's happening. Explaining the influence of wellhead pressure. Okay, those were for unconventional resources. This is for conventional resources. This is wellhead pressure and frac gradient versus production. So x-axis is wellhead pressure. Each curve shows a frac gradient. This is explainable AI. This one is AI, but it's non-explainable, the black box. Question, this is exactly the same well that they did it for, or the same area that they did it for, or the same field. On the left, you can see clearly well-behaved. Do you see the same thing on the right-hand side? No, that's where you do it with, when you don't do it with explainable AI, you do it with black box. I'll give you another example. X-axis is pay thickness, y-axis is production, and every curve shows eastern location. Explainable versus non-explainable AI. X-axis is shot density, how many shots to the casing. Production, average injection pressure for hydraulic fracturing. Explainable versus non-explainable AI. You see how does this look? Cluster spacing for each curve. Average wellhead pressure. On x-axis, production in. You can clearly see the differences. So the last item, let me talk about ethics of artificial intelligence. I'm going to take only a few minutes on that, then I'm going to go to the geoanalytics to show you how this application in one of the things that you probably deal with a lot. So some of the non-engineering real business application of artificial intelligence, facial recognition, voice recognition, they have impacts on people. AI-based models are vulnerable. Remember I said the physics-based model that we make, if you use it correctly, it must avoid assumption, it must avoid biases, right? Question, can you include assumption and biases in AI model? Yes, you can. AI-based models are vulnerable to assumption and biases that can be introduced by its human creator through the data that is used to train the AI system. Facial recognition algorithms made by Microsoft, IBM, Face++, all had biases when it came to detecting people's gender. They were able to detect gender of white men more accurately than gender of dark-skinned men. They called racism that. In 2020, study reviewed voice recognition developed by Amazon, Apple, Google, IBM, and Microsoft found that they have higher error rates when transcribing Black people's voice than white people's voice. In 2014, 2015, Amazon used an AI hiring requirement technology. What happened? The algorithm favored male candidates over female candidates. Those were racism. This is sexism. This was because Amazon's system was trained with data collected in 10 years period that came mostly from the men candidates. The data was pushing it in that direction. Amazon, when they found that out, Amazon terminated their AI hiring requirement in 2019. Companies such as IBM, Google, and etc. have made efforts to research and address the bias of AI models when they found out. One solution for addressing bias is to create documents for the data used in training of AI systems. MIT, Massachusetts Institute of Technology, created a whole AI ethics group that they're doing a lot of work on. This is from an article written by MIT. It says, the problem of bias in machine learning is likely to become more significant as the technology spreads to critical areas like medicine and law. I personally added and engineering. They didn't have that. And as more people without deep technical understanding are tasked with deploying it. Some experts, that's what I've been saying it for 20 years. Some experts warn that algorithm bias is already pervasive in many industries. Industries use a lot of engineering. And that almost no one is making an effort to identify whether it's correct. So many industries, they're literally talking a lot about engineering. Will Knight from MIT says, Google's AI chief says, forget Elon Musk's killer robot and worry about bias in AI system instead. This is where it came from in 2019. That said, I'm going to finish it right now by showing you AI ethics in petroleum engineering, what they call hybrid model. In the context of AI ethics, inclusion of assumption and biases in petroleum industry is done through what they call hybrid model. When data generated through mathematical equation is combined with actual field measurement to train the AI-based model, what does that mean? It means that the company, that service company that everybody knows their name, 3 of them, and a lot of vendors that they say they AR based. Ask them, you know why they're using hybrid model all the ways? Why? Because they tried to build AI-based model using the actual field measurement, and they were not able to do that. They were not successful. Then what did they do? Therefore, they would generate data from mathematical equations that includes assumptions and biases and has a pattern already. They combine it with the actual data so that their machine learning algorithm works. Let me show you a simple example. You see this data? This is from a conventional field in offshore South Asia, a project that we're working with. So oil production in y-axis versus gas lift on the left, completion in the middle, and porosity on the right. You see what the data looks like. This is another one from onshore field, Marcellus Shale in Pennsylvania. What you're looking at is well productivity in y-axis, stimulated lateral length, total number of stages, and total proppant. You see what the data looks like. Literally when they build hybrid model, these big companies, this is the data they have, and I showed you an example of it. They cannot build the model. What do? They use an equation and they generate data, and they combine it with that. They generate more and they combine it with that. Hey man, we got a pattern. We got a complete pattern. This is my AI solution. That's why it's a hybrid model. That's why it has nothing to do with reality. That ends my presentation. And I'm going to use the last 10, 12 minutes to show you this geoanalytics, the latest thing that we have developed to see how we use AI to do what we do. And then we open it for any questions that you have. Very quickly, we built top-down modeling, which is AI-based reservoir simulation. So AI-based reservoir simulation takes an opposite approach when it's compared to the traditional numerical reservoir simulation we have been using for 60, 70 years. Let me explain it to you. Let's assume this is a field, and here is the formation that all these wells is drilled down there and completed here in order to produce oil, right? This is called the bottom. Why? Because formation is 10,000 feet under the ground. And then what do we do in traditional numerical reservoir simulation? We'll provide that information to a geologist, geophysicist, petrophysicist, G&G experts, and we tell them to build a geological model for us. They build a geological model, they'll give it to the reservoir engineers put it in CMG or Eclipse or any software, right? What is the objective? To history match the production up here. Production shows here, right? How do they do that? They modify this geological formation that was given to us by G&G. Why? Because we are reservoir engineers, we are not wrong, right? G&G people who built the reservoir and gave it to us, they're wrong. So I have to change that to get a history match. That is traditional reservoir modeling, which is a bottom up. You go from bottom, you go to the top, up where the oil is. So bottom up modeling starts with space, as you see, then brings in the time through mathematical equation. That's traditional numerical reservoir simulation. What is AI-based reservoir simulation? AI-based starts from here, starts from the top. It uses the measured historical production from the top first. And then it goes and history matches this production, trying to figure out what this looked like, what this reservoir is. So instead of starting with the space, then going to time, it literally does exactly the opposite. It starts with time and goes to the space. That's why we call it top down rather than bottom up. It starts with time and then brings the space through field measurement. So with that, the traditional numerical reservoir simulation first uses a basic and original geological model developed by G&G. The traditional numerical reservoir simulation that is developed using G&G by geological model, it never, ever, ever results in a history match. You all know that, right? What do you do? In order to get a history match, you actually end up going to every single well. You change the transmissibility around every single well until you get a history match. So the geological model is modified. So if I put it in a very simple fashion, a numerical reservoir simulation starts with the original geological model, tries to history match, but it never does the history match. So it goes a transmissibility modification for every single well in order to, and it modifies the original geological map, and it goes over and over and over and over, continuously do that until you get a history match. Once you get a history match, you succeed, then your new geological model is very different from the original one that you were given. And then, of course, you can use that to do optimization of production. That's the traditional numerical reservoir simulation. Now, let me show you what we do as geoanalytics. So in traditional numerical reservoir simulation, first, the basic geological model is developed. But the key behind it, guys, is that they develop the geological model, G&G people. They use well log, they use core, they use seismic, they use assumption and interpretation. But the key is they use spatial interpolation. They interpolate between the wells spatially, purely based on space. How do they do that? Using Kriging or radial basis function. Very, very simple example. This is a spatial interpolation. If you have 3 wells, each one of them has a value of porosity, then you got to find out the distance between them, and then you identify what's between them. That's spatial interpolation. And this, what you're looking at here, this is an actual field in Southeast Asia, offshore. These are the existing production wells. These are the injection wells in that particular field. And of course, if it's spatial interpolation, you just get the distance between wells, producers or injectors, and then you create this. If you have gamma ray for every single well, spatial interpolation allows you to generate a gamma ray for the entire, correct? Now, let's see what we do. What we do, one more last thing. So in traditional numerical reservoir simulation, you start with a geological model, modeling the reservoir formation, and then use that in order to build a reservoir model, which is modeling fluid flow in porous media. In AI-based, you do exactly the opposite. You start with the reservoir model, fluid flow in porous media, and you try to come up with a geological model. That's what we call geoanalytics and top-down modeling. So instead of spatial interpolation, it does the spatial temporal interpolation. How do we do that? We use the static data and the dynamic data. We use the dynamic data in fuzzy pattern recognition, and then we use the fuzzy pattern recognition and more dynamic data to generate what we call dynamic conductivity map. I'll show it to you in a minute. Then we use the dynamic conductivity map and both dynamic and static data in order to create the spatial temporal interpolation. And then all of that provide us the geoanalytics or AI-based geological model. Here's how it works. This is the same field that I showed you, producers and injectors. First, what do? We take for every single injector communication with all the producers. This is for this injector, this is connection with the other one, or interaction for every single injector with all the, this is all the injectors interaction with all the producers, number one. Number two, we go to every producer and we know every producer is interacted with all the offset producers around it. For this one, so we do that for every single producer and identify its offsets and the communication that they have. And we put them all together. This is all the producer interaction. This is combining all the producer and injector interaction. Once we have that, then we identify the conductivity, that connections identifies the conductivity through fuzzy pattern recognition, which is detail of it is explained in the book called Shale Analytics that we, anyways. This is the conductivity map that is generated for that field. This is only shows the time, the dynamic data provides this. Then you use this. And remember, this is the gamma ray without conductivity map, only by space interpolation. This one is exactly the same data. However, it's using spatial temporal interpolation. Why? Because it's using conductivity map in order to provide distribution. This is for, so on the left is traditional, on the right is geoanalytics. This is gamma ray. This is density. This is clay volume. This is resistivity. This is formation top. This is thickness. This is porosity. This is permeability. This is initial water saturation. See the difference. Now, we use the same technology and we do what we call dynamic mapping of remaining reserve. So in this particular field, which is again in Southeast Asia, we identified what is the original oil in place in stock tank barrel. Not only that, but we know based on this dynamic mapping, we know where, how it's this original oil in place, how has it been distributed using conductivity map. And then this is original. This is in May 2020. Now I know where the sweet spots are. we do that on a monthly basis. If you see this video, it shows you month by month how the distribution of oil in this field is modifying, is changing. After we do that, then we do it for pressure. This is original pressure in 1997. This is the pressure distribution in June 2020. And again, here in a video, we'll show it to you on a monthly basis. Look at the difference. Look at how the pressure changes as a function of time on a monthly basis. When you have this for every layer reservoir, and you have it for every. Now, this is my last slides. I'm going to show you when we use geoanalytics and top-down modeling, what the result is. What I'm showing you is a presentation in a panel by the top manager of a company that we did the TDM for. And believe me, I had no idea that this had happened. When he presented it at ATCE in 2020, I was shocked that I asked him, am I allowed to share that with people? And he said, yes. And this is exactly what they showed, not me. This is 2 years after we did it. So what you're looking at, this is in Caspian Sea, Turkmenistan. As you're looking at here, these are 4 wells. These 4 wells, 3 of them, 198, 195, 178, they were, the location was identified by numerical reservoir simulation. The one in the middle, 193, this was done by TDM. Now let me show you results. So in April 2020, they checked it out. This one in 178 was drilled in February 2013. This for 86 months until 2020. This one was in 2014, 65 months. This one, these 3 were from numerical reservoir simulation. In 2015, 62 months. TDM, that's when we did the project for them. We finished it in June 2018 and asked them where to drill. We didn't even know that they drilled, but apparently they drilled it, and 22 months. This is the result, folks. This is the highest production rate only in the first 6 months in barrels per month. So this one, the first 6 months, the highest production was 51,000. This one was 41,000. This one was 53. The TDM was 76. And then for the entire production, dividing by total number of months, these 3 were numerical reservoir simulation. This was TDM. Okay, that ends my presentation. I'll be happy to answer any question that you may have. Sorry, it was a very long presentation.
Awesome. Thank you so much, Professor. Thank you for your great presentation. Maybe you already answered some of the questions, especially in your last 3 articles in your LinkedIn. And you answered many questions. By the way, Sefidet asked a question, and the question is it correct to generate data by simulators for AI or ANN learning?
Actually, it depends the problem you want to solve. The answer is yes. However, it's a different problem. The top-down modeling, which is building numerical reservoir simulation, not numerical, AI-based reservoir simulation, is only applied to mature field. And for mature field, the answer is no, you should not get data from simulator. You only must get it from field measurement. However, if you're going to build it for a green field, which has hardly any wells, and you want to start it, then you do a numerical reservoir simulator first, then you get the data from the numerical reservoir simulation, and you can build a smart proxy model, what we call it. And why would you do that? Because if you have a 3, 4, 5 million cell for a numerical reservoir simulation, and even if you use the HPC, it's going to take you 10 to 12 hours on HPC to make a single run. But if you build a reservoir, a smart proxy model, that I said, the data from numerical reservoir simulation, build the AI-based model, you can get a model cell-based for every single cell. You get results which are up to 95% accurate. But the difference is you can run it on your laptop in 2 minutes rather than on an HPC for a whole day.
Okay, thank you. And another question for you is from Anton. He's wondering what is your view on Harvard bias top-down modeling approach? I'm not sure if I the Bayesian learning, where the efforts around reducing the wide range of prior geological models and
I
yeah.
Sure. Is it possible to have them ask the question themselves?
You can just ask
Unmute.
your question. You can turn on your microphone and then.
Right, thank you. Thank you for your presentation. So I'll try to ask this question myself. So there are similar efforts in terms of deductive versus inductive modeling in geophysics, and it's called Popper bias top-down modeling, also called Bayesian evidential learning, where the efforts revolve around reducing the wide range of prior geological models and scenarios, and falsifying those unprobable or unlikely probable geological concepts before proceeding to any calculation of the final quantities of interest and decisions. What are you familiar with this approach, and is it in line with the petroleum data analytics?
To be honest with you, no, I'm not familiar with it. I'm very glad to hear that from you and learn that, and I'm going to follow that up. I didn't know they geologists do that. It's very interesting. However, as long as the geologists use only space interpolation and not a spatial temporal interpolation, then that separates and differentiates what I presented in terms of geoanalytics. That I know for a fact, communicating with some of the geologists here in the companies that I've done some work for and here at the university, that they do not do spatial temporal, and everything is purely a spatial interpolation. However, the difference, if they do even only a spatial and they have a difference between deductive versus inductive, then definitely the inductive is going to be far better. But still, that's one difference. The difference that I mentioned had to do with time and space rather than deductive versus inductive. I hope that makes sense.
Yeah, all right. Thank you.
Thank you.
So, Tamer, you can ask the question. Tamer?
Yeah, I'm just unmuting myself. Okay.
Yeah, because I put my laptop far away from me to cover, the camera. It's very hard for me to read your question. You can just ask.
Okay. So yeah, thank you, Dr. Shahab, for this great presentation as usual. So apparently, you don't prefer this kind of hybrid modeling, in which we integrate the physics and the AI. So what about using the physics to constrain the AI modeling? Are you okay with this approach? Like how do you see this kind of approaches? Like we depend on the physics and physical equation to constrain our AI modeling.
My immediate reaction to that is to ask how. How would you constrain it? Because if your objective is constraining it, I have absolutely no problem with it. However, if in order to do that, you're going to generate data from your mathematical equation and add it I don't think, actually, I just show it to you. It's really, it has really nothing to do with AI and machine learning. But if you can do this constraint that you mentioned, I have no problem with that. Actually, I like the way you mentioned it, to be honest. it's something to think about. Is it possible to do the constraining without generating mathematics-based data? Then it's great to do that. But how?
Yeah, I didn't think before about how, but what I see, because usually, for example, when we deal with log data, sometimes we have indirect measurement, right? And this will be hard for the AI, like let's say the neural network, to get the correlation, for example, between this log data and the relative permeability. For example, and the average permeability. If we want to have this kind of correlation between the log data and the average permeability, and we want to implement the neural network, for example, in this case, it will be hard, right? If we use just the direct log data for this one. But if we manage to use kind of well-known correlation.
Not really. If you send me an email, I can, in 1993, that's my first article that I wrote had exactly to do with what you just mentioned. Trying to figure out or coming up with permeability using well logs, using actual data without making any mathematical equations. Because I'm sure you're familiar that when you plot porosity versus permeability, you get data all over the place, and people just draw a single line and they say that's it, which is, when you do with AI, you don't do that anymore. You can find a lot of detail from multiple logs rather than just one log or one porosity, and come up with a solution. And we have, I had a lot of master's degree, did their masters on this with data from multiple places that they're all published, and you're most welcome to take them. It can be done in that fashion. And in that specific, I know how to handle it without mathematical equation. But what you mentioned from a reservoir engineering point of view, honestly makes sense to me. And I'm going to give it a lot more thought to find out. Until now, we couldn't come up with that idea of how to constrain using certain things that we know. So, but one thing that I would ask you to think about is, if you have actual data, don't you think, number one, don't you think the actual data are representing the physics? Number one. Number two, if the answer is yes, then don't you think any constraint that exists can be included in that constraint, in that actual data or not? I think there might be. In other words, maybe what you're looking for, you can find it from the actual data. If it's not, your model gives you results that doesn't make sense, then you have to come up with a way to handle that. I'm not sure how. One thing I know for a fact that it's very negative is to generate data through mathematical equation, because when you do that, you're no longer using AI.
Mm-hmm. Yeah, okay. Yeah, because you see, like doctor, if we have, for example, as you mentioned, for the average permeability and we have the log data, we know that there is a kind of correlation between the short resistivity and long resistivity and the depths of invasion, right? Or the invasion depths.
Yes.
So in the problem formulation and the long resistivity, it will be hard for the neural network to get this relationship. But if we externally, we got the depths of invasion using the short and long resistivity, and instead of this, we provide the neural network with the depths or invasion depths. It is much easier for the neural network, to get.
Absolutely. There is no problem as long as you don't generate permeability by that. But that's called feature generation, feature engineering, actually. So that's why domain expertise is incredibly important, because if you're teaching the machine learning algorithm and AI how to come up with permeability using short resistivity and long resistivity. Then you can add different things to it by making calculations and include depth, so there is one more thing that we always talk about. There is explicit data, there's implicit data. Explicit data are all the ones that we use through mathematical equation, through our experience, and come up with the solution. Implicit data are the data that usually we do not directly use in mathematical equation, but maybe they have some sort of an interaction. For example, gamma ray could have some sort of interaction with resistivity to help. So many different things, because even if they don't, then you can find out from the connections between neurons that you do, you can find out which parameter that you provided actually is helping to build the model or to train the model versus not to do that. So feature generation is an absolutely good thing as long as you don't use the features to generate output, but just add it to the input.
Yeah, thank you, Doctor. Thank you.
Sure.
Okay, so Professor, I think it's my turn to ask questions.
Please.
So one thing, I did many projects in petroleum industry, in geosciences, in handwriting recognition, medical, but I was wondering, I think you already answered that in your slides, but we have geostatistics and we have big guys in this field, and they are claiming that the variables are spatial, they are distance dependent. Okay, so in an intelligence system, how I think you indirectly involve distance in your AI modeling, right? I'm just wondering how we can involve distance in our intelligence systems. I think maybe I'm wrong, but I think that the advantages of geostatistics is involving distance. It takes the variable as a spatial variable. It's space dependent, But in intelligence system, when we want to train a model, if we input the distance, for example, the distance between the whales, for example, as the input data, it's wrong. I tried that. It doesn't make any sense. If you want to insert the distance between the wells or the eastern or northern in your modeling, it's like, it's weird, based on my experiences. How we can involve distance? Is it should be directly, insert the distance in your input, or we have to just come up with the thing that you did in your modeling, like the dynamic conductivity map. You use that kind of map to cover the distance between wells. So what do you recommend when we want to involve the distance in our modeling?
Okay, so again, in general, it all depends. One of the major key about using AI to solve a problem, to a very, very large extent, has to do with the objective and the solution that you're trying to find out. And as a domain expert, your objective and the solution you're looking for is going to tell you how to teach, using the data, how to teach all the details to the algorithm as much as possible. So one thing is for sure, I don't know what was the outcome or output or the target of what you were talking about, if it's production.
For example.
Therefore, the distance plays a role. The distance between every well and its offset wells play a role. Does that everything? No, absolutely not. If you're thinking about distance has to do with the porosity and permeability between the distance, of course, you're absolutely correct. It's not only distance, it has to do everything that happens between the distance. If there is a fault, the distance could be very, very, very short. The fault doesn't allow anything to happen, right? So the key is, number one, you're not providing one piece of information, you're providing a lot of pieces of information. And the key is, it all comes down to what problem you're trying to solve and what, for example, if you are trying to find out production from every single well at every time step. The time step, number one, what defines time step for you? Your data. If you have the data for every day, you can use time step daily. If you don't, and you have it only monthly, then your time step is monthly. So if that's what you're looking for, if you're trying to find production for all the wells on a monthly basis, then the question is, what causes that? Well, space and time. What in space, what in time? You find out all the first thing, you can come up with an incredible number of variables for that. But you cannot use those variables unless they have been actually measured. One item that I'm going to just mention here to all of you guys, because as reservoir engineers, what do you need? You need flowing bottom hole pressure, right? Does anybody measure that? Historically, not today. No, they don't. So what do? If you want to do a history matching, we use production as an input and we calculate flowing bottom hole pressure. That doesn't work in numerical, in AI-based model. Why? Because such a measurement doesn't exist. What does exist a lot of time? Wellhead pressure, choke setting, flow line pressure. Those are easily measured. You don't have to spend incredible amount of money to send something down to measure flowing bottom hole pressure. That's why it doesn't exist. So you always limit it to whatever existing measurements you have. Then you have to use your expertise to find out how to represent your measured data, to what degree, to how. One of the things I showed you for the system to learn. So one of the things I just showed you in geoanalytics is, one of the things we found out is that every well at every time step is communicating with the wells around it, right? It has to do with distance, it has to do permeability, it has to do porosity. But then all you have to do, find out, if I take the history of this and history of this well next to each other and plot it against each other, if I get a pattern, I say something is going good. If I see exactly a negative pattern, that it's no, what does that mean? That means they have nothing to do with each other, right? And I'm not making that decision. I'm just doing that, generating the data and giving it to the AI to figure out if there is any communication between them or not. I hope that answers your question.
Awesome. And my second question is that exactly you just mentioned. We use different kind of data with different dimension, with different facility to be taken, with different resolution, different nature. I know we use all of those data. We normalize all of these data to come up with the same value for all of them. Yeah, that's right. But in intelligence system, as long as we can follow what is in the nature, we will come up with the better result, So I just was thinking about it. Is it, we all do it, but is it correct to use, for example, well lights, R-column, S-cal values, seismic, all of these different data, they are different in everything, nature, resolution. Is it correct to use all of them in a single model? I'm thinking about it for more than 4 years.
To be honest, the answer is yes. However, there is one major problem with that, which is called, what did I call it? Because what determines, so hypothetically speaking, what you just said, the answer is yes. Use as many as you can. However, if that provides you with 100 variables or columns of the data, then it all depends with how many records do you have. Because you cannot use one, if you have only 200 records data, you cannot use 100 variables. You have to use only 20 maybe.
Yeah.
So you have to come up with, there is a whole different process through which you can identify, out of all the data that you have, all the parameters that you have, which ones you should use, which one you should not use, which one you should use, which one you should try not to use, actually.
Got you. And my last question, other people have also questions. Your top-down modeling doesn't result a unique answer, right?
Unique?
answer, a unique model with a unique result.
What do you mean? What do you mean by word unique?
If you use the production data and then trying to create the physical model, the geological model, so it's not, I think it's not possible to come up with just one physical model based on those production data, right?
No, there is no you don't come up with one mathematical equation, but you come
No
up with
equation.
one physical model. Yes, there
Yes,
is only one model.
Only one model that matches with those production data?
Exactly. You have one model, this one single model that you developed at TDM. You history match every single well with exactly the same model. And that is that's one of the major differences. When we talk to people at the different companies, when they ask us, we tell them, okay, if you want me to build a model for each well, that is AI-based decline curve analysis. I can do that, but it has nothing to do with go back to reservoir simulation and reservoir modeling. Reservoir simulation and modeling is one model that you try to get the entire field, every single well. It includes all the producers, all the injectors, everything, right? That's what TDM is. TDM, you don't build. That's one of the reasons that some people are using LSTM to use literally to do AI, they call AI based, I call it AI based decline curve analysis. They call it reservoir modeling. It is not reservoir modeling. Reservoir means the entire system. So it is one model of the entire system that is applicable to every single well and in its past and doing the future.
Okay, I can understand, but other people are in the line.
Sure.
James, you can just ask your question, please.
Sure.
Yes, thank you very much. It was a wonderful presentation. I dialed in from France here. I want to ask a question, I'm concerned with the fact that there are some recent trends in AI application that I really think about and feel like they are doing something very fantastic. But based on your opinion, I want to know what way to go. For example, even though the primary essence of designing convolutional neural networks and LSTM for image recognition and natural language processing per se, but in the context of reservoir engineering, I see some application where convolutional neural networks are used just to be able to learn the 3D spatial form of the reservoir, and then the combine with the LSTM to capture the temporal. So you see something like a spatial contemporary kind of combination between CNN and the LSTM, and then they even go ahead to give you a result that looks very fantastic, and you ask yourself if this is really what we should look up to, or what is your opinion about that?
I'll tell you what my opinion is. I'm completely against that.
Yeah.
And let me ask you one question. As a petroleum engineer, as a geologist, when you were trying to figure out the quality and the characteristics of the reservoir, here's my question. Did you send somebody down there 10,000 feet underground to take a picture and bring it up to you and you look at it and say, great?
No.
Did that ever happen?
No.
No. So how do we generate the map? We don't do it through pictures. We do it through calculations. We have cells, 1 million cells, and we get the value of the porosity for every single one of them. We talk about it, we do it in a different fashion, but that's how generates the map, how that generates. So the way that a picture is generated for reservoir, it is not based on taking a picture, my friend. It's based on calculation and expertise of modeling. However, The convolutional neural network is not that. Convolutional network is only about picture. And that doesn't exist. And when people do that, it's one of the two problems. They either are not reservoir engineers, that they don't understand that, or they are reservoir engineers, but they don't understand the AI and how that works. So if you go through convolutional neural network, what does convolutional neural network does? What does the word convolutional means? It combines things, it identifies and combines. So when they take a picture of a person or of some whatever that is it that they're trying to convolutionally build a neural network for, when they take a picture, that picture has pixels, 100 by 100 pixels, 200 by 200 pixels, right? The question, if it's 100 by 100 pixel, one picture has how many input? 100 times 100, that's 10,000 input, right? One record has 10,000 columns, variables. Does that work? No. That's why they came up with convolutional neural network. What they do, they use digital signal processing of that 100 by 100 pixels to identify the first, they do 15 of them, 15 layers of that. First one, they try to find all the lines that go flat. Then they do it again, they find the lines that go vertical. Then they do another one, they do circles, blah, blah, blah. So they do all of that, 15 of them. Then they have 15 curves, 15 lines, and they convolve them. And if it's, let's assume they're doing it human face, then they know that nose is always in the middle between the eyes, not above the eyes. The mouth is never above the nose. It's always below the nose, right? So they come up with this and they know these curves and they convolve them. So out of 20 layers, 15 of them are digital signal processing to find layers, and then they convolve them in the 5 layer of neural network. That's what they call it, convolutional neural network. However, when we're already dealing with time and space. Therefore, every piece of information, the production, the oil production, every barrel of oil that you produce, is it only about time or is it only about space? Neither one of them. It's a combination of them, right? It's already convolved. So what you have to do in reservoir engineering in TDM, you have deconvolutional neural network. You have to provide both space and time and make it learn how to separate space and time. Because if you keep one thing in mind, when you provide historical data for every well, do you get a straight line? No, you get up and down, up and down, up and down, right? It's
yeah.
But when you drill a new well on your TDM, you're still going to get that? No, you're going to get a straight line. Why? Because the space stays the same and the one thing in time is only changing. The same is true in numerical reservoir simulation. It is impossible. And then when you do LSTM, my friend, LSTM is only about time. It doesn't bring in space. So literally that is the decline curve analysis. That's why it's only done for one single well. Of course, there is a new version of it that we do in reservoir engineering, which is different from what they do in non-engineering application. So the bottom line is, if you get good results on that, believe me, it's not a bad thing from an academic point of view, but for it to be able to predict anything, because that's what the key behind when you do it for a company, I can guarantee you're wasting a lot of time.
Thank you. Thank you so much.
Thank you. Hassan, you can go. Something, ask your question, please.
Yes. Hello, thank you. Thank you very much, Dr. Shao. I wanted to suggest something that also Hossein brought it up. It was about if you have too many data columns of a reservoir, maybe 100 columns or 200, There is, I just find out about it. There is a funny method. You can actually reduce the number of them. So you at the same time you can reduce the time of program running, and also you can maybe even increase your quality of your work. It's dimension reduction actually. It tells you what parameters actually works better for you as input to get the output you want.
Sure.
I just wanted to mention it's an interesting thing. And the other thing about your method, AI method for reservoir modeling that you suggested, I just wanted, if you can explain please a little more what exactly happened in there. You said the method was bottom top. I just want to what exactly we did in there. Our main input was the production data, right? I'm not sure. What
Production is output.
is the output?
Yes.
So the input was the pressure or
A lot of time, it depends whether you have pressure measurement. The input is definitely one of the things. I'm going to give you a very quick example, but I have written a book on this topic, published by SPE, called Data-Driven Reservoir Modeling. So that's the best way. It's a whole book. It's very hard for me to explain it in a few sentences. But literally the output is oil production, gas production, water production, and sometimes even pressure and saturation are output, not input. The input is all the static information. There are two types of static information. We call it well-based and we call it polygon-based. And because every well, the measurement that it comes from it logs, it's only 6 inches away from the field, sorry, away from the well. But then communication between two wells has to do with the information of the static information between them. That's what geoanalytics help us to do. Of course, geoanalytics is not in that book because it's recent thing that we have developed. But nevertheless, I think the best way is to look at it is through that book rather than for me to be able to explain it here.
yeah, sure, thank you. I just wanted to ask if you have a paper or book about this. I'm
Oh
sure.
God, yes.
Sure.
If you send me an email, I will send you an AI primer for PDA, which includes incredible amount of links to videos, books, papers, and stuff that you can access to and read them if you're interested.
Fantastic, sir. Thank you.
My pleasure. Thank you.
Okay. So, Tamer, you have another question?
Yeah, I have another question. Yeah, doctor, and this mainly for the LSTM, because you know you mentioned it several times, and actually I'm planning to use it now on one of the projects I'm working on. So I'm just wondering, I agree with you that the LSTM is not, is somehow is similar to the decline curve analysis we use because it captures the memory effect, it captures what's happening during the time, right? But what if we manage to add also the space as input for the LSTM? For example, you mentioned, especially for unconventional reservoir, the LSTM cannot detect if there is a communication or interference with another well, right? But what if we have the LSTM and we train this LSTM, including even the distance to the nearest well, right? And by this one, you know, so it is totally different than the decline curve analysis, right? Because the decline is just the decline rate, right? This
yes, yes, that's a good point, Tamer. The only thing is, as long as you do not build the model for a single well, because if you do it for a single well, the distance or any static information is not going to change as a function of time, correct? It's going to be, so that column only have one value. And when you put it in the one value, you normalize it between 0 and 1, and it's going to be all 0. So it never contributes at all to your, and actually it's going to confuse your model, and your model is just going to kick it out. And it's going to be there, but the model never use it as long as you do it for a single one. But if you do it for the entire field with 100 wells, let's say, then you have that distance for every well. Every well has multiple offset wells. That distances all come in. Then there is not one value. Then it's a good idea. That's actually how we have used it as well.
Okay, so you are not completely against utilizing the
No, at all. That's one of the things I tried to say. Not only I'm not against LSTM, I think it's fantastic. I'm not even against convolutional neural network that James asked. You must learn convolutional, you must learn LSTM, but keep one thing in mind, they were developed for non-engineering application. In order to use them in engineering application, you just provided a very good example. You have to do differently. They never do that in LSTM when they developed it for natural language processing.
Yeah, or stock market.
Exactly. So what you definitely, they're good. They're fantastic. You have to learn everything Google and Facebook and others do. You must learn it. No doubt about it. However, the only thing you don't have to do, just don't copy paste. Use exactly the same thing to solve your problem. No, learn it. That learning tells you how to solve your problem. You don't need only to learn the A, B, C, how it goes. You need to learn the idea, the philosophy, the approach to problem solving. Then use the same ideas in problems and solve your problem. Not exactly the same step that they took. Why? Because the problem is different, but they are so expert in AI and machine learning, 10 times better than I ever was going to be. So, but I'm going to learn from them. That's the key issue.
Yeah, thank you, Doctor. Thank you. Totally agree. Thank you.
Awesome. So I think now, okay. So we are done. Would you please just everyone, if it is possible, turn on your camera to take a picture from the end of the meeting, please, just in case if it is possible. I just want to take the picture in 3, 1, 2, and 3. Awesome. Thank you, everyone. Thank you. Thank you for joining us today. And thank you so much, Professor Mohammed. It was a great pleasure to have you today. And yeah, that's all. That is it. Have a nice day and have a nice night, maybe somewhere.
Have a great evening, everybody.
Take care, guys. Take care.
All right, bye.
Bye. Take care.